We did normal logs, we did modeling logs, and now let's try it with graphs. Bella, this one's on you. As I mentioned in my previous video, logs in general have a very standard way of laying out the problem. The first is to turn an exponential into a logarithmic equation. Take logs of both sides, split the logs using log AB is equal to log A plus B, and then you can bring the t down because if you have log A to the power of 2, for example, then you can write it as 2 log A. Simple 2 marks, nothing too different. The next bit gives you a graph and asks you to find what is P and what is Q. If you pay attention to the equation, it is simply a y equals to mx plus c, where c is equal to log P and m is equal to log Q. So find the c-intercept and make it equal to the log base 10 of P, which gives you 7,940. Next is log Q. This one is slightly more tricky as you need to find the gradient, but realistically, not that hard. And when you do it, you get the gradient as 0.03472, and rearranged, Q becomes 1.08, and the P was 7,940, as I mentioned. Using the model, figure out when her house will become £500,000. Whenever they ask you for the time, it is a lot easier to use the log equation rather than the exponential. So rearrange your log equation to figure out at what time B is equal to 500,000. You can do it one at a time, or you could just rearrange first and then input the values like I did, giving you 53.828 years. This is after 1970, so 54 years later means 2024. Ah, interesting. So give or take around now. Lastly, is this value reliable? Let me check. Well, considering the prices of houses in the UK, yeah, that sounds very accurate. Okay, if I'm being serious now, you need to say that the model assumes a constant growth and is not affected by things like market crashes, which are unpredictable events. Another thing is that this value extrapolates outside of the range of values that we have in terms of time, meaning that it may not be completely accurate. So even when you have logs with graphs, it's just as easy as before.